Hi, this is a video on some further terminology in metric spaces, in particular neighborhoods, accumulation points, and so-called adherence points as defined in Terence Tao's analysis book. I will go through these definitions. We will state a theorem relating to these, and then we will prove that theorem. So, a neighborhood of a point X in a metric space X is any open set that contains X. So O subset of X is a neighborhood of X in X if two conditions are satisfied. X is inside O and O is open. So there's no other constraints in this class. There are different ways of defining neighborhoods, but this is a very common definition. And usually we imagine these neighborhoods as being small, but the crucial thing here is that there's a little bit of room around X. That's common in all of these definitions, whether they're defined slightly differently or not. So an adherence point is a point X, an adherence point for a set E, is a point X in X, and this E is a subset of some metric space X, depending on the context, such that no matter the ball radius you take, for every radius positive, then the ball of radius R intersects E in a non-empty way. So, in other words, for every R positive, there exists some Y such that Y is contained in the intersection of this ball. That's another way of stating this condition. So this is sort of like a boundary point, but it includes also points that lie in the interior in terms of what we have defined before. So if my set is something like this, so the solid line is included in the boundary, the dotted line not, and examples of adherence points, this one, A, this one B, and this one C. But then these are yes examples. So these are adherent. But points that do not satisfy it, points out strictly outside, D is not. Why? Well, here there exists a radius such that BX R intersect E is empty. Whereas for the other points, no matter the radius you choose, whether small or a little bigger, they intersect the set. In the case of A and B, this is because A and B are actually inside the set E. So this observation means that E is always a subset of adherent points of E. But additionally, boundary points also satisfy this because boundary points, no matter the radius, they intersect the set E. They also, the radius will intersect the complement, but here for adherence, we only insist on a part of the assumption of being a boundary. That's why we get new points as well. So you could think that these are points in E plus points that touch or are adherent to E. Now, some books define a very closely related notion of an accumulation point, and this is defined slightly differently. So it's a very similar idea. It tries to remove the points A and B from that previous picture. So X is an accumulation point of E if for every radius R positive, the ball X R intersected with E, and if we take away X, that this is not empty. So in other words, for every positive radius, there exists a Y that's not equal to X, and this is where we make the condition slightly different, such that Y belongs to the BXR ball intersected with E. So to give an example, suppose my E is, say, 0 union 1, 2, then the adherence points are just 0 union 1, 2, all of the points in E. But the accumulation points, these are just the points 1 to 2. And why is this? Because this point, the 0 point, is a so-called isolated point, the set E. So if we draw this, we have 0, then we have the interval 1 to 2. And if we take a sufficiently small radius around 0, so there exists a radius, say 1/2, so that if we take the ball center at 1/2, centered at 0 with radius 1/2, then the intersection with E is just equal to 0. And this means that there is no other point. So that's not an accumulation point. On the other hand, if we take the point 2, say, then for every radius R positive, the ball centered at 2 will intersect E in a way that excludes 2. E.g., we could take a delta equal to the minimum of R over 2 and 1/2, and then 2 minus delta would be in E, intersect B to R, but 2 minus delta would not be equal to 2. So that would be the proof of this case. So this is a point that both of these points are touching the set 0 and 2. They are actually elements of the set in this case, and that's why they are adherent. But one of them is an accumulation point, and where this term accumulation comes from is that we can actually, the set somehow accumulates to it. That is, we can find a sequence of points converging to it. Now, to get a sense of these concepts, and this is a good exercise for most of the concepts in metric spaces, is that there are some basic theorems that relate these concepts to each other. This is one of these theorems. This is copied from Terence Tao's book. If X is a metric space and you have a subset of X and you have a point in X, then the following are equivalent: that the point is adherent to E, that the point, second claim is that the point lies in the boundary or in the interior, that it lies in the union of the two. So it connects this notion to the boundary and the interior. And the third one connects this notion to the notion of convergence, meaning that there exists a sequence of points in E such that it converges to X. Now, one remark is, in C, we allow a constant sequence. So what this means is that, for example, if X is in E, then we can choose xn just equal to X for all n natural number, and then limit as n goes to infinity, xn is equal to X, because it's just the limit of a constant sequence. At its distance, xn to X is equal to 0, so limit n goes to infinity, distance xn to X is just equal to 0, which is the definition of convergence. So yes, so this allows a constant sequence that plays a role in the proof. Accumulation points do not allow for constant sequence, so one has to be more careful. Another thing I want to say is that you often see statements about the following are equivalent. This is often abbreviated as TFAE. And the way to prove that is often that you go through a cycle of implications. First, you prove A implies B. Then you prove that the second condition implies the third, and then you close the loop by going back from C to D. There are different ways of doing these, but this is the most common way of doing them, is that you put these conditions in a chain and then you prove the implications. This way you minimize effort. Instead of proving first that also B implies A, or that C implies B, the other directions, these don't have to be proven because they become automatic from the proof. So in this, we don't do these directly, but they are implicitly proven, because say if we want to go from B to A, well, we can go from B to C. We can conclude from C A, sorry. And then from A to B. So this gives us a way of cyclically going through these claims to get what we want. So this is how the proof is then structured, and this is often how the following are equivalent proofs are ideally structured. So A implies B. This means that x0 is adherent, implies that x0 is at the boundary, or x0 is in the interior. So let's check this. What does it mean to be adherent? It means, let's first fix x0 and x adherent. I'll abbreviate ADH to E. Well, by definition, there exists a radii, by definition, sorry, not exists, for all radii, positive radii, and it's important to have positive radii here. If we take the ball of radius r, then this intersects the set E in a non-empty way. Now, there are two cases. Either BXR is all of the elements in the set are contained in E, or either there exists some radius such that this is the case, or this is not the case. So the complementary claim to this one is that for all radii positive, we have EXR intersects E complement in a non-empty way. So these are two cases, and they're complementary because if we call this P, then this is just nothing else than not P. And for every proposition, we have that P or not P is true. So one of these claims has to be true. Either there exists a radius, so the set is contained in E, or no matter the radius, you also intersect the complement in a non-empty way. So let's see what we get from these cases. In the first case, there exists a radius, such positive radius such as Bx0r is contained in E, but this means that by definition, x0 is inside the interior of E. This is the definition of interior, that there exists a radius such that this holds. So we have proven one of the parts. In case one, we are in the interior. Now in case two, no matter the radius, we intersect the complement. Well, since the point is adherent, we also have that for all radii, the ball radius r intersects E in a non-empty way. So now what we have this, then by definition of boundary of the set E, what we have is for every r positive, both Bx0 r intersects E is not empty, and Bx0 r intersects E complement is not empty. This is the case that we have, and this means that x0 is in the boundary of E. And this is done because we have shown that either we are here, which is case 2, or we are in the interior, which is case 1. So B implies C. Now, if you take a point that's either in the boundary or the interior, we want to construct a sequence that lies in E and converges to it. Now, the assumption has two claims. Let's fix an x0 in boundary of E, union intersection interior of E. And let's consider two cases. Well, either x0 is in the interior. This is a little bit easier, so first. Or case 2, x0 belongs to the boundary. Well, if x0 is in the interior, then there exists a radius positive such that Bx0r is contained in E. And well, x0 is contained in that, so x0 is also contained in E. And then we have to show that there exists a sequence. So we choose xn equals x0 for all n in natural numbers. My natural numbers, by the way, here don't include 1, so there's no issue in defining x0 as equal to x0, even though that would not really be conflating the notation. So xn is equal to x0 for all n. This is what we define. Now, limit as n goes to infinity of the distance of xn to x0 is limit as n goes to infinity of 0, which is 0. So by definition, limit of the sequence of elements xn is equal to x. And we're done with case 1. So we found a sequence. In this case, it is the constant sequence conversion to it. Now, if we are in the boundary, the case is a little bit different. So what we have is for every radius positive, the ball centered at x0 with radius r intersects E in a non-trivial way. So no matter the radius that we choose, we can find a point inside. And we can do this for different radii because we have this for all r. So the idea now is we want to construct a sequence. We'll apply this for different radii. So choose for each n, we have, by assumption, that bx0 1 over n intersect E is not empty. So there exists a y that is contained. So there exists a y that we will directly, there exists an xn that is contained in bx0 1 over n intersect E. This defines a sequence in E. So xn is in E, well, because it's always chosen to be in there. If there exists, you can make these choices. This technically uses the axiom of choice, but since we're not doing set theory, we will not highlight that. You can make infinitely many choices in this class. So this defines a sequence in E, but now, well, distance xn to x0 is always less than 1 over n, and it's bigger than or equal to 0. So by squeeze theorem, limit n goes to infinity, distance xn to x0 is equal to 0. So by definition of convergence, xn, limit of xn is equal to x0. So this constructed a sequence that converges to the point. Now C implies E. If you have a sequence, we want to prove that it's adherent. So let's finish this part. Suppose that there exists an xn in E such that a sequence of points xn in E such that limit of xn is equal to x0, i.e. limit n goes to infinity, distance xn of x0 is equal to 0, because this is the definition of convergence. We have to use the definition, what it means to converge. Now, what we want to show is that it's adherent. So for every r positive, bxr, x0r intersect E is not empty. And the idea is that these xn are getting closer and closer to x. They lie in E. So we will use those, but for a large enough n. And again, now we're proving for all r the conclusion. So let's fix an r positive. There exists a n such that for all n bigger than or equal to n, distance xn to x0 will be less than r, definition of limit. Now this is the definition of the limit of a real sequence. So pick y is equal to x capital N, then distance y to x capital N is less than r. So y is in bx, distance y to x0, sorry. So distance from y to x0 is less than r. So by definition of the ball, y is inside this r radius ball, and xn, y is equal to xn, is also in E. So now it's in both of these sets. So by the definition of intersection, y is in the intersection of E with the ball bxr, x0r. And we're finally done. Because what we did, from the assumption, we were able to conclude that for every r was arbitrary, we found a point here So E intersect BXR is not empty. And we're done because we found a point inside. Okay, so this was a video about adherence points, accumulation points, and their relationships to boundaries and interiors.